Okay. So far, we've been talking about how this applies, so how you can figure out the magnetic force that is acting on like a single moving charge. You could imagine that the same exact thing would apply if I had a current moving through a wire. Or, I mean, really, you saw sort of in this demonstration, this was not just a single charge, right? It was like a stream of charges that were moving in the vacuum tube, right? And so you saw the effect of the external magnetic field. So just like you have the magnetic force is just QV cross B. There is this version of like figuring out what the magnetic force is if you have like current going through some length of wire L, right? So here, this L is just referred to as a length vector. Okay, and the length vector points in the direction of the current. Okay, so like if I added up, like if I add all the force acting on like all of the charged particles in like a current, then I would get this. Does that make sense? So it's like looking at it from the point of view of like single individual charges, but now I've got a lot of them and they're moving through a wire, and I want to figure out what is the magnetic force acting on that wire. I could just sort of add up all of the individual Lorentz forces, and then, you know, a way of calculating that would be the current times the length vector cross B. Okay, so it's like taking it and applying it to like a larger scale. And I mean, the right-hand rule is exactly the same. So if I've got the current that is pointing in this direction, and I've got it going into the page, right? So current into the page, the force vector is up. Does that make sense? Okay. So we've got a demonstration. Actually, maybe I'll do this one demonstration and then we'll take a break. So we've got a demonstration set up here. And this is basically like, here, I'll draw it for you. So you've got a wire that's like this. And then there's this large kind of magnet like this. And you can think of like the magnetic field is going across like this. And we said that it's going from, so this is the north side of the magnet, and this is the south side of the magnet. So it's going like into the page, the magnetic. This is a large, a very, very strong sort of U magnet. So this is the north pole, the pink side, and this is the south pole. Right? So remember, outside a magnet, the field lines go from north to south. So the field lines would be pointing like into the board. So we could put this arrow here just to remind ourselves. Okay? And the current, we're going to connect this battery up. And the current goes, this is the so it goes from positive to negative. Right? Okay. So what would you expect to happen to the wire when I turn the current on? So I've got current going through, and so current going through, I turn the magnetic field on because it's in a strong magnetic field. You would expect the field or the force to be pointing down, right? So it should get pulled down. Okay, and if I change the direction of the current, you would expect it to go up, right? For the same reason. Okay, so current is going this way. Okay, So the current's going this way, okay? The magnetic field is going that way. So in the first sort of rendition, you would expect the force up, right? So current cross B, force up. So let's see what happens. Okay, does that, I kind of looked away. Did it go up? Okay, all right, so, okay, so what if I change, so let me just do it again because I missed it. So it goes up, definitely, right? So if I change the direction of the current, just by changing these wires, then you would expect the opposite to happen, right? So let me put this wire back in the B field. So again, the B field is pointing in the direction of the arrow. Now I've got the current going in the opposite direction, right? So now the current's going that way. The B field is still going that way. So now the force should be down. It's not as like impressive, but it is definitely down. Okay? I'll just leave that. Okay. So any questions on that or anything so far? No? Okay. So let's take a break. I think like if we come back at 7:45 and we'll pick up at that point. Let's pick this up again. So we're going to go through this exercise together, and then we've got exactly this scenario set up on the floor. So we'll show it to you afterwards as a demonstration. Okay, so I've got this large truck battery that is connected to a long wire, and you can actually see, for those of you who are sitting in a spot where you can see it right here. So that's the truck battery, and then it's connected to this long wire that's kind of stretched around, and you can imagine that it's kind of like in a rectangle, right, like on the page. So the current is the flow of positive charge. So the current is going to be like this, okay? So let's consider just the top part of the wire. So just this part of the wire. And we want to know what is the magnetic field created by just that part of the wire everywhere in space. So which of the two right-hand rules that we've talked about so far do you think that we should apply? The first one. Good. Okay. So I'm going to put my thumb in the direction, of the current, right? And so my fingers are the magnetic field. So the magnetic field is going to be coming out of the page on top and going into the page on the bottom of the wire. Okay, so I'm going to draw that on here. So that's the direction of the current. So it's going into the page. Sorry, it's coming out of the page here. So I'm going to put dots here to indicate that it's coming out of the page here. And it's going into the page there. And this is just from the top wire. Okay, and you would expect it to sort of extend down below this wire as well. Okay, so does that make sense? So current is going in this direction. It's coming out of the page on the top and going into the page on the bottom. Okay, so now the question is, what would be the magnetic force acting on the bottom wire due to the magnetic field created by the top wire? Okay, so what I want to know is, like, if I were to draw a magnetic force on this part of the wire, which direction would you expect it to act, up or down? So let's see. So I put my fingers. So here, now I have to apply the second right-hand rule, right, to figure this out. So I put my fingers in the direction of the current, which is this direction here, right? So fingers in the direction of the current. It's coming out of the page, right? So I would expect the force to be acting down, Does that make sense? So the magnetic force is going to be down like this. Right? So let's see. So into the page, down. Right? I put my fingers in the direction of the current, so that's this direction. I curl them in the direction of the magnetic field, so that's going into the screen. Okay, and then the magnetic force acting on that bottom part of the wire is acting downwards. Does everyone see that? Okay, so now we want to, so that's the force that I drew there. So now we want to do exactly the same thing, but with the top wire. Okay, so let's draw, if I were to draw the magnetic field as a result of the top, or the bottom wire acting on the top wire. So again, I'm going to put my thumb, I'm going to use the first right-hand rule. I'm going to put my thumb in the direction of the current, so that's this here, right? And the field curls into the page in the middle and then out of the page below, right? So it would be like this. All the way up, like I would draw this field here. Right, and then down here it would be coming out of the page. Does that make sense, using the first right-hand rule? Okay, so what about the wire, or what would you say about the force due to the magnetic field from the bottom wire? So this is the bottom wire magnetic field. What do you think the direction of the force would be on the top wire? So let's do it. So the current, okay, and here it's going into the page, right? Okay, so I've got my direction, so I've got my fingers pointing in the direction of the current, right? I curl my fingers towards the magnetic field, right? And so where would the force be acting? Up, right? So the force on the top wire is going to be up. Does that make sense? So current, curl them towards, into the board for the magnetic field. My thumb is the magnetic force. So acting on the top wire, there's an upward force. Yeah? No? Okay, so just literally look at my hand relative to the screen. Okay, I'm talking just about the top segment of the wire right now. Okay? I'm putting my fingers in the direction of the current, right? I'm curling them in the direction of the magnetic field. The magnetic field is going into the screen at that point up above, right? So the magnetic force has to be pointing up. Does everyone see it? Okay, so the combined effect, therefore, would be what? If we were to turn this truck battery on, what would you expect to happen to the two segments of the wire? They would jump apart, right? Because both forces are acting sort of, outwards. Okay, so let's try it. So will the wires attract or repel? They're probably going to repel. Let's see. Okay, so we've got a camera. And we're going to put these two arrows on the floor so you can see the direction of the current. Okay, so the direction of the current, not that it matters, but the current is going this way and then this way. Okay, through that. Yeah. See it? Okay, so let's turn it on.
Okay, here we go. So watch the wires. 3, 2, 1.
Pretty cool, right? Okay, so does that make sense? Did anyone have any questions? No? Okay.